Okay, we're going to pick up where we left off on Wednesday. I introduced the 4 addition reactions to alkenes. That's what we're doing here. 4 addition reactions to alkenes. So we are reacting the alkene with a compound. It's going to add across the double bond. Now, Leah, this is a classification of reactions. There's going to be 4 different ones here. They're falling into this classification. And this contrasts with, I'm mentioning Leah because she asked me the question on the quiz, what do you call that reaction? When bromine reacts with an alkane, we call it a substitution. This is different. We're not substituting, we're adding. It's not that something's coming off the molecule and something else is going on. That's substitution. This is that every bit of this reactant is going on the molecule, adding to it. That's why we call it an addition reaction. There's going to be 4 of them. They're going to be named after the reactant. And the thing I want you to pay attention to, 2 of these reactions are symmetrical molecules, and 2 of them are unsymmetrical. And that's going to come into play a little bit in trying to predict some of the details of the outcome of the reaction. We looked at this one on Wednesday, and we were looking at this. We said this hydrogen, it's like a hydrogen molecule, is going to add across that double bond. It's going to get rid of the double bond. And that's where you're going to get these 2 hydrogens. There's hydrogens there too. I mean, it came with 4 hydrogens, and it ends up in the product with 6. So ethene becomes ethane. Converts an alkene into an alkane by hydrogenation. By the way, you have come across this term. Just go into HEB and start looking at the peanut butter. Turn it over, look at the ingredients. Some of them will say peanuts. Isn't that comforting? You see a jar of peanuts, and one of the ingredients is, or peanut butter, and one of the ingredients is peanuts. But some of them will say peanuts and partially hydrogenated vegetable oil. They're doing this reaction to things like corn oil or canola oil. They're partially hydrogenating it. Set that one back on the shelf and get the one that says peanuts. All right? If you want peanut butter, you might as well eat peanut butter. All right? The other one has partially hydrogenated vegetable oils, and that is a possible source of trans fats. You could get some trans fats in there, where they're saying no trans fats. If it says no trans fats and it says it's partially hydrogenated, I would bet any money you could find some trans fats in there. It might be less than 0.5 gram per pound, or I'm not sure what. I think it's a less than 0.5%. If it's less than 0.5%, they can say there are no trans fats in there, but there are. The peanuts probably don't have any trans fats in them because they have not hydrogenated that. But that's where you come across it. Partially hydrogenated vegetable oils. This is what they're doing to it. Yeah, and we looked at the way this proceeds on Wednesday. This double bond is made up of 2 electrons. This bond, 2 electrons, and those electrons just shift into a new bond and dissolve this bond, dissolve that double bond. You don't no longer have an alkene, you have an alkane. Here's the general thing. We're going to have, so hydrogen was the first one we looked at. We're going to have three more, excuse me. So the next one is a halogen. And these halogens can be fluorine, chlorine, bromine, or iodine. And what you notice about the halogens is just like the hydrogen, they are diatomic. These elements are all diatomic molecules. This is the way they exist as an element. Neon doesn't do that. Neon exists as a discrete atom. It's not Ne2. It doesn't bind to itself. But for various reasons, these all bind to themselves and form diatomic molecules. So when I'm using this term here, symmetrical, what I mean by that is these molecules, doesn't matter which one I look at, if I split that in half, the two halves are the same. So the molecule around this bond that's holding it together is symmetrical. And what does that mean? That means that each carbon in the original double bond gets the same thing. Okay? So you don't have to worry about, where does the hydrogen go? Well, a hydrogen goes on each carbon. Where does the fluorine go? A fluorine goes on each carbon. A bromine goes on each carbon. You follow me? So these are a little simpler because they are symmetrical. So if we had ethene, and we come along here with fluorine, it proceeds just like the hydrogen. I mean, I could come over here and say essentially the same thing is happening. An electron is moving up here from the double bond and forming a carbon-fluorine bond. The other electron from the double bond is shifting down into here, forming another carbon-fluorine bond. That eliminates the fluorine-fluorine bond. It eliminates one of the bonds between the two carbons, and you get a molecule like this. It's got a fluorine on each carbon. So ethene became 1,2-difluoro, so ethene becomes, plus fluorine, becomes 1,2-difluoroethane. It doesn't become 1,1-difluoroethane. It's not that the fluorines both go on one carbon. It's 1,2-difluoroethane. Each one of the original carbons in the double bond gets a fluorine. Okay, this is a little worksheet. Don't get scared. You want to pick up paper. Bring them out of the quiz. This is a worksheet. Do the first two reactions. They're going to be hydrogen and bromine reacting with propane. So finish those two reactions. Use pencil. This will get you to. So we're going to. I've given you ethene. You take it up to propene. What would you get if you reacted these with propene? And don't worry about the bottom two reactions. Don't go there yet. Okay? If you go there, you might assume it's just as simple, and it isn't. So just do the top two reactions. And if someone wants to run up here and do these two, do one of them. We will eventually do all 4 reactions, but let's just do 2 at a time. So we have this. Okay, all you got to do is just draw the product. And leave room down here. Leave room down here for these last 2, which we'll do in a minute. Save your classmates so I don't have to call on anybody.
Do you have to draw it sideways like that?
However you want to draw it, kind of try to fit it in here if you could. Yeah. When I draw it up and down, I'm just doing that to kind of show you where the electrons are going. This is usually the way we write chemical reactions. Okay, you got these 2? What do we get? What's the product? Propane. Here's where our 2 hydrogens are going. Nothing else changes. We eliminate that double bond. We've got 2 hydrogens here. We're adding them across the double bond and we get propane. This is what we had originally. We had a double bond right here. So what do we get here? A bromine and a bromine. All right? So we get a bromine on each of those double bonds. They're not going to both be on the end. They're going to be right there. If this is something else, wherever the double bond is where this gets added. Okay? Just keep that in mind. Don't just say, oh, I got to put 2 bromines on that molecule. You got to put them on where the double bond was originally. Okay. So we've done hydrogenation and halogenation. The next thing to add to this is H2O. So what can we call that begins with an H? Hydration. Just like a runner that needs to be hydrated, needs to drink some more water, this is adding water to an alkene. Now, we're going to look at this water. We're going to look at this water like this. I mean, the water is this. But we're going to only really be particularly interested in one of these hydrogen-oxygen bonds, because it's one of these bonds that is going to break and the hydrogen is going to go on one carbon, and the other part of the water molecule is going to go on the other carbon. So you can see if we focus in on this bond right here, we sever that. This is not a symmetrical reactant. It's unsymmetrical. Half of it is a hydrogen, the other half of it is an OH. All right, so this is hydration. Hydration. Now, here's what really happens in real life. And Mark Konikoff was the guy that really started looking into this. So we take propene, which we've been reacting over here, propene plus water, and you can see that, oh, here's my propene. I could add the hydrogen there and the hydroxyl there, or I could add the hydrogen there and the hydroxyl here. There are two options. This hydrogen could go on the end, and the hydroxyl could go in the middle of the molecule, or the hydrogen could go in the middle and the hydroxyl on the end. You see that? Now we've got, because the molecule is unsymmetrical, the two parts of it are different, gives rise to two products that can be formed. Here it is where the hydrogen went on the end and the OH went in the middle, right where the double bond was. You get the hydrogen here and an OH here. Here is where the hydrogen went in the middle and the OH went on the end. Mark Konikoff did this. He did these reactions. And I don't know what he expected to find. I think if I went in the lab for the very first time and had never gotten into these and said, oh yeah, you could get two different products. And if someone said, I'll bet you Coke that it's 50-50, I'd say, well, I bet you Coke it isn't. I had a boss one time. We would make these polymers. He had about 30 years experience over me. And then he would say, I bet it's this viscosity. And I'd always lose. I always lost. And then we'd walk down and he'd get a Coke and he'd drink it and say, oh, it always tastes better when someone else pays for it. He was a great boss. All right, he was a great boss. But all right, so I would, two possibilities there, and I would think, well, seems to me they're both possible, they're both equally as likely. We'll get 50% this and 50% this. So Mark Konikoff did these experiments, separated out the products, and said, whoa, we get a lot more of this. 85%, maybe 90% of the product is this. 10% of the product is this. This is why he said, okay, that's our major product. This is our minor product. Keep in mind, Mark Konikoff isn't deciding how this is going to happen. He's investigating what's going on here. And he's finding. This is empirical data. This is where you go in the lab, you do something, you see what the results are. So he did it with other alkenes. He did it with a bunch of alkenes. And there are many of them where there's two possible products. And he got different amounts of them all. And so he came up with Mark Konikoff's rule, which helps predict what is going to be. I mean, after he did this 12 times, he said, I'm going to pull up this rule. I'm going to try it with a new alkene and see if I could predict what will be the major product. And he was able to predict it. All right, so we're talking about, you see here, acids here. Water is a weak acid. HCl, HBr, HF, HI are strong acids. HOH is a weak acid. It's water. It's neutral. But there is a proton and there is a hydroxyl group. This is what makes water acidic. It's what makes it basic. And you form an alcohol. So Dmitry Markovnikov, a Russian chemist, observed many of these. And he came up with this rule, that the hydrogen of the acid most often goes to the end of the double bond, which had more hydrogens. So hydrogen is going to the place where there's more hydrogen. And the OH, or the other part of this molecule, whether it's the OH, the chlorine, the bromine, the fluorine, the iodine, goes to the other carbon in the double bond. So this helps you predict the major product. Hydrogen goes to the end of the double bond that has more hydrogen. Does the saying, the rich get richer, does that help you? Do you see? The rich, the carbon that has the most hydrogen gets more hydrogen. The rich get richer, if you want to put it down that way. We could probably argue about that, but seems like it might be the case. Okay, let's go back and look at these two products and see if that's what's happening. Here's the major product. Where'd the hydrogen go? It went to the carbon that had two hydrogens on it. It did not go to the carbon that had only one hydrogen on it, at least not most of the time. In most of the cases, the hydrogen went to the carbon with the most hydrogen, and the OH went to the other carbon. That's the major product. Okay? Simple rule, but when you're hydrating, this is hydration, or hydrating a double bond, you need to think about Markovnikov's rule, particularly if the question says, draw the major product. You've got to figure out what is the major product going to be. All right, so here's propene again. Here's HBr. HBr. So we're down to the fourth one now. HX. X is a halogen. So up here when it was hydrogen, we called it hydrogenation. When it was halogen, we called it halogenation. Here we're going to bring in both of them. Hydrohalogenation. We've got both here. So this could be HF, HCl, HBr, or HI. Hydrohalogenation. And you can see these are just like water. They're unsymmetrical. You got a hydrogen on one side of the bond and a halogen on the other side of the bond. Just like water, the hydrogen goes to the carbon with the most hydrogen, and the bromine goes to the other carbon. That's your major product. What's the other product? That's your minor product. Does that happen? Yes, but 90% of the time, you're getting the major product. Okay, I want to just go back to our original one here. Notice the name of this, isopropyl alcohol. Isopropyl. That's one propanol. The OH is on the end, or propyl alcohol. That is like an isopropyl group. And where is it attached? The OH is attached in the middle, right where an isopropyl attaches to a chain. You all have a bottle of this at home, I bet. What else do they call it? Rubbing alcohol. is isopropyl alcohol. It's cheap. Don't drink it. All right? Not good for you. Just goes to show you, anything with the name alcohol on doesn't mean it's an alcoholic beverage. That's rubbing alcohol, but it's cheap because that's your major product. This one is going to cost more. All right? It's harder to make. You don't get as much. You only get 10% 1-propanol. You get 90% isopropyl alcohol when you hydrate propene. Okay, go ahead and finish that last one. This last one here. You can finish both of them. But we've kind of done them. I probably should have, on this worksheet, given different molecules in order in the slides. Okay, you're going to add HCl to this double bond. So the H is going to go on one carbon and the Cl is going to go on the other one. What goes on the end here? The H. And the chlorine ends up in the middle. All right, why? Because this one has 2 hydrogens on it. This one only has 1 hydrogen on it. We come back here to our original double bond. We've got 2 hydrogens here. We've got 1 hydrogen here. All right, the rich get richer. Not that the rich need to be defended, but because they don't. But Warren Buffett, and people familiar with Warren Buffett? Trying to remember the name of his company. Yeah, he's a billionaire, and it's well, at any rate. He's very, 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 very wealthy, but he has, for years, he's said, raise my taxes. He says, I'm not paying enough taxes. There's a rich man that's saying, raise my taxes. So, and he's been trying to get other people to say the same thing. My taxes are too low. And I mean, he's willing, and I mean, he's philanthropic, so he will give a lot of money away, but he's basically telling the government, you know, yeah, I'm wealthy and I'm making money and I can make more money, but you should be raising my taxes, not other people's taxes. I'm just trying to remember the name of the company. It's oh well. Yeah. He's kind of an investing company. He has he's up in Iowa, and he has enough money to pay a lot of people to research all the companies out there and find out what's the best stock to buy and stuff like that. What? No, it's not Fidelity. I'll think of it. All right. Let's look at a couple of. Oh yeah, there's an enol. Let me just. Since acetylene came up there, let me just mention quickly what happens with a triple bond. Okay, this is ethine, or its common name is acetylene. What happened to my slide? I keep threatening to try to fix this. I guess I never get the time to do it. This one is, you need to know this molecule by both of these names. And this one is a little bit tricky because, and this trips a lot of students up. I say draw acetylene, and they'll give me an alkene. Because, well, what have you learned? You've learned that an ENE mending is an alkene. But here is the one exception, okay? This is acetylene. It just has a poor common name. It makes it sound like it's an alkene, but it's not, and it's an alkyne. It's got a triple bond in it. Well, if I come along here and react this with hydrogen, I will get rid of one of the double bonds. And I'll get ethene. I mean, if I start out with a molecule that is C2H2, and I just add H2 to it, I'm going to get a molecule that's C2H4. It's that molecule. With me? So, but it reacts very similarly as an alkene. The hydrogen adds across one of the triple bonds. Gets rid of one of the triple bonds, you got a double bond. But what does this mean? Well, you can come along here with another hydrogen, and so you're adding two more hydrogens here, and what do you get? Well, we look at that reaction. This is ethene plus hydrogen forming ethane, C2H6. So you've gotten down to an alkane. The point of this slide right here is that alkynes undergo these same reactions, but it requires 2 moles of these reactants to eliminate the triple bond and to get it saturated. So really, ethyne plus 2 hydrogens forms ethane. Not one hydrogen, not one H2, but 2 of them. All right? So just keep that in mind. And then this slide over here is just talking about water reacting with an alkyne, and you get an enol, you get a ene for double bond, ol for alcohol. Don't worry too much about that. Okay, let's take a look at these 4. Predict the major product in each of the following reactions. Well, let's look at A. What is the major product going to be? If I add hydrogen to what I got right there is trans 2-butene. What's going to happen to this double bond? It's going to go away. And what is it going to get on it? Each one of those is going to get a hydrogen on them. And the double bond's going to go away. So you're going to have 2 hydrogens there. And methyl's out there. So that's CH3, CH2, CH2, CH3, which is butane. So butene becomes butane. There isn't a major and minor product. It's the only product. It's the only product. Why? Because that is symmetrical. There's only one product. This one is symmetrical. You're going to get a bromine here and a bromine here. And you only get one product. you say, well, which bromine is that? It doesn't matter. One bromine goes there, one bromine goes there. They're the same. They're identical. You get one product. So there's no major or minor. But if you come over here and look at both of these reactions, you do have unsymmetrical reactants. Let's look at B. I'm going to lay B out here a little bit differently. All right, now I'm laying this out, and I do a problem like this. I say, well, okay, I need to think about Markovnikov's rule, so let's lay this out on a piece of paper. Am I finished here? Does this get a hydrogen? Does this carbon get a hydrogen on? No. How about this one? Yes. So I can put a hydrogen on here. 1, 2, 3, 4 bonds around that. This has a hydrogen. This carbon has one hydrogen. This carbon has no hydrogen. Which carbon has the most hydrogen? This carbon. 1 is greater than 0. Markovnikov's rule says the hydrogen is going to go on the carbon that has the most hydrogen. And the OH is going to go on the other carbon. So you're going to get a hydrogen here and an OH here. And you're going to get rid of one of those bonds. That's the major product. Major product.
So before we put hydrogen somewhere else, we have to put it on the carbon that has hydrogen.
Well, that has the most hydrogen. That one was the most. Well, let's look down here. Yeah, before you put anything else on there, find out where that goes. Figure out where this goes. Where is this hydrogen going to go? We got a carbon-carbon double bond. Is it going to go here or here? 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 That has only one hydrogen on it.
And bonds to the other ones each.
Okay. So we're going to put the hydrogen here and the chlorine here. And we'll get rid of that.
It would go to the CH3.
No, that can't take any more hydrogens.
Oh, yeah.
And there's no double bond there. The reactant has to go where the double bond is, nowhere else. We didn't study these reactions in chapter 10 because alkanes don't undergo these reactions. We're studying these in chapter 11 because these are characteristic of alkenes. I think we got this here. Of course, they gave you the answer. Yeah, they gave you the answer here in stick figures, but it's not as pretty or as easy to see. Okay, there's one more reaction of alkenes, and then there's we need to discuss and describe aromatics, and we'll have chapter 11 finalized. Okay, this is commercially very important reaction. $1 trillion industry is making plastics. Are they very expensive? Plastics are fairly cheap, but we make tons of them. The water bottle made out of plastic, the trash bins made out of plastic, the chair, the bumper on your car, the markers, the computer keyboard is just plastic everywhere. All different kinds of plastic. So how do we make plastic? The general thing is the polymerization of alkenes. This is a very versatile reaction to produce all different kinds of plastics, depending upon what alkene you are polymerizing. Ziploc baggies, milk jugs. We're going to look at where these plastics come from. Here's kind of laying it out. There's your monomer, your beginning alkene molecule. And you are polymerizing it. It's an addition polymer. I don't exactly know how I expect you to write this out, but let's think of our simple alkene here for a second. I'll tell you what, I'm going to write this. I'm going to write the hydrogens right above it like this. This is ethene. And just imagine a bunch more of them lined up here. And what happens? This is a hot reaction. Exothermic reaction produces a lot of heat. You have to control this reaction, or it'll melt down your kettle. What they do is they start out with an initiator or some sort of a catalyst, but some sort of initiator. It might be, it'll generate a free radical. What's a free radical? Any compound that has, any atom or compound that has an unpaired electron, which they are very, very reactive. They slam into something, they want to pair up with another electron. So this electron comes in to pair up with this electron, and you get a bond. So you're going to get on one end of this polymer is going to be your initiator, and then it generates, that electron comes up in here, generating a free radical. It slams into here, forms another bond, and then you get another bond and another bond, and you start eliminating these things. So you can see that each one of these started out as an ethene, the monomer. It started out as ethene, and you get 2, 3, 4, 5. But this polymer is growing 2 carbons at a time. So it goes from 2 to 4 to 6 to 8 to 10 to 12, 14. And so then they would characterize this as this. They draw the monomer, say there's bonds coming off of there, and they put the letter N right here, which is the degree of polymerization. Like if N was 1,000, this polymer would be 2,000 carbons long. See that? You'd have 1,000 ethene units in there. It'd be 2,000 carbons long. It had gone up 1,000 times, and then they would end it off with something. There'd be some sort of molecule entered or something already in there that would cap it off at 1,000, and you'd get it, instead of a gas, ethene being a gas, you would end up with a solid. And you heat it up, it would melt, and you could make it flow and turn it into films and inject it into molds and make things out of it. This is polymerization. Well, here's one thing you make out of it. You get this out of rubber trees, 2-methyl-1,3-butadiene. It has 2 double bonds. So this is going to, an electron is going to come over here to start the initiation. That electron will come into here. This electron will come into here, form a double bond, and that electron comes out here to propagate the polymer. So there's your repeating unit. And you do that 1,000 times, add some carbon black to it, and you have automobile tires. You inject that stuff into molds and heat them up and vulcanize them, cross-link them, and you've got rubber tires for automobiles. So that's another polymer. Here is, this is nylon, polyadipic acid, nylon. Let's not worry about that one. That's a little bit more complicated, so don't worry about that one. Here's Teflon. This is tetrafluoroethene. So you got an ethene molecule, but instead of hydrogens on it, it's all fluorine. And you polymerize that. N could be 200, 1,000, 10,000, whatever. And you get Teflon. You get this polymer that is non-stick in nature. All right, so if you take a peek at these codes, the one at the top, PETE, that's what you should find that triangle with a 1 in it on the bottom of your water bottles, like this, polyethylene terephthalate. So they're taking ethene or ethylene from crude oil and terephthalate, the terephthalate molecule, and polymerizing those together. That's your monomer unit now. And you get polyethylene terephthalate. Here's Ziploc baggies. Low density polyethylene, PE standing for polyethylene. Milk jugs, which are higher density, more rigid, high density polyethylene. So both of those are polyethylene, just different molecular weights, different degrees of polymerization. Polyvinyl chloride. There's your repeating unit. You started out with ethylene, but it had a chlorine on it. And now when it polymerized, every other carbon has a chlorine on it. Here's your monomer unit, degree of polymerization, and you get plastic water tubing for home water supplies. So if you don't have copper or metal pipes in your house, you have plastic pipes, they're probably polyvinyl chloride pipes. Polypropylene, polystyrene, the white insulated stuff. So different monomer makes a different plastic. So there's a lot of variety, a lot of different plastics you can make just by what you start out with. That styrene, you'd have started out with a molecule like this. And we'll get into the aromatics right now, or in a minute. So you'd end up with ethylene, but you have a benzene ring. And now on every other carbon, there's going to be a benzene ring, a benzene ring, a benzene ring. You get polystyrene. I don't know what they got here. Ketchup and syrup bottles. It says other. Generally speaking, if it's other, I don't particularly like it in contact with food. So I don't know what they're talking about there. Ketchup and syrup bottles. But what would also fall in this class is polycarbonates, which are not good for food. They were making baby bottles and different plastics out of polycarbonates. And you put them in the microwave and you could leach things out of them, like bisphenol A could leach out of them. Polycarbonates are used for the plastic glass, like in a screen door. In case you didn't want glass in there, they'd use polycarbonate. So polycarbonate has a use, but it's not generally with food. No, you don't have to remember these. I think what you need to remember here is that alkenes, a general reaction of alkenes is polymerization. And if the question were, by what reaction are most plastics made, it's the polymerization of alkenes. Okay? I expect you to know that much. I probably won't have you be mapping out reactions like this. I mean, that's kind of hard to write a reaction like that, but that's how the reaction proceeds. Okay, that brings us to the last topic, aromatics, and let's see if I can cover this. You are already familiar with cyclical compounds. That's cyclohexane. We also, in chapter 11, said, you could have 6 carbons in a ring with a double bond in the ring, and that is called cyclohexene. But now we're going to look at a special case here where we have alternating double bonds inside the ring. This is aromatic. Cyclohexene and hexene will both undergo hydrogenation pretty much the same way. You add a hydrogen across the double bond. Aromatics won't. There are certain characteristics now about this molecule with these alternating double bonds that puts them in a class of their own. Even though you're looking at double bonds, don't think you're just looking at a standard alkene. Okay? It's not. These are aromatic. And this particular molecule here is benzene. It's your poster child of aromatics. It's the most commonly known aromatic molecule, benzene. You can see it only has one carbon only one hydrogen going to each carbon. Because you have that alternating double bond, you've got 3 bonds going to every carbon now, and you only need one hydrogen. So the molecular formula is just C6H6 for benzene. There are lots of aromatic compounds, and some of them are very, very nice. This one isn't. This is a carcinogen, but vanilla is got aromaticity in it. Oil of wintergreen that's in chewing gum is got an aromatic ring in it. Okay, Kekulé, a German chemist, got looking at this, trying to understand what's going on with these molecules. Just know here, these are 2 resonance structures. You can see that double bond is here. It's moved over one, so it moved every double bond over one, but I still have a 6-membered ring with alternating double bonds. They are identical drawings. They're resonance structures, so either one. And we tend to look at it more like this. We just draw a circle inside of it to indicate that it is aromatic, that ring has alternating double bonds in there. It's not like this is a double bond and that's a single bond. It's more like this is 1.5 bond, 1.5, 1.5, 1.5. They're all the same all the way around there. So is it really a double bond sitting there? Well, probably not. It's more like this. We say that there's a bunch of electrons here. There's 4 there, 2, 4, 2, 4, 2. Well, the electrons get delocalized or up into a cloud above and below that ring. The ring is flat. It's a 2-dimensional flat molecule with a cloud of electrons. The molecular orbitals above it and below it, called a pi cloud, or using the mathematical symbol pi cloud of electrons above it. It generates a particular stability to this molecule. So there's these overlapping orbitals. These are all different ways of drawing benzene. This is its IUPAC and common name. It's benzene. It doesn't have any other name that I know of. I don't know of any other name. Don't call it tri or cyclohexatriene or anything like that. This is benzene. Okay? But these are all different ways of drawing it. Structural. Here's a line diagram with the alternating double bonds. Here's a line diagram with the circle. So this and this are identical or mean the same thing. Okay, so I said that was benzene. If you put a chloro group on it, you have chlorobenzene, nitrobenzene, ethylbenzene. Here's the one. This is one you do need. You're going to need 3x5 cards for all of these, but for right now, in chapter 11, this is carbon and hydrogen. This is toluene. This is benzene with a methyl group up there. So that is better known as toluene than as methylbenzene. It's a very common organic solvent called toluene. So you should put together a 3x5 card for that. I'll be adding these others as we go into the other chapters, but just for right now. Know this, that if benzene is on a ring, so what we got here, look, we got 1, 2, 3, 4, 5 carbons. So we got a molecule like this, 5 carbons. And on this carbon here, we have a benzene ring. So what are we going to call that? Oh, I got too many hydrogens there. Well, we're not going to call that benzol or anything like that. We're going to call that a phenyl group or a phenyl substituent. All right, so you can see how we've named this. This is 1, 2, it's 1, 2, 3, 4, 5, so it's pentene. It's 1 pentene. The ene starts on the first carbon. It's 4-phenyl 1-pentene. So here is another alkyl substituent, a phenyl group. Okay, we just have a few minutes to finish up chapter 11, which we'll do on Wednesday. Your chapter 11 homework is due when you arrive, and we'll barrel into chapter 12. Okay, so the slides are up there.